Imagine a single tube whose stiffness, geometry, and material chemistry changes along its length and is all extruded as a continuous part. That sounds like science fiction, but that is what the next generation of catheters and minimally invasive devices actually demand. So why are most medtech designers still gluing and using heat shrink? To talk about this, I brought in Simone Maccagnan. Simone is the business development manager at Gimac International, a family-owned Italian company his father, Giorgio, founded in 1983. For more than 4 decades, Gimac has been pioneering precision and microextrusion and co-extrusion for medical tubing. In this episode, you're going to learn how microextrusion replaces multi-part catheter assemblies with single continuous extrusions, and why that matters for validation, scrap, and patient safety. What dynamic co-extrusion really is, and where the physics get difficult, and what it unlocks in terms of next-generation catheter design. And then we will talk about what augmented intelligence, how Simone calls it, is starting to help operators handle lot-to-lot polymer variations and shorten medical device process validations. My name is Lucas Pianegonda, and I've helped over 40 medtech companies to be more sustainable with plastics. Here's our discussion. This episode was sponsored by Gimac. Hi, Simone, and welcome to the podcast.
Ciao, Lucas. How are you doing?
Yeah, so Simone, you are the son of the founder of Gimac, a high-tech medical extrusion machine company. Tell us a bit about what your company does and what your technology can do.
Okay. Thank you for inviting me, first of all. Gimac is producing since 45 years extrusion equipment, which we design, test, and we develop the processes on top of those equipment. And we do this since more than 40 years now. The early 80s is when my father started. So our extrusion equipment has been, as far as I know, the first used for making microinvasive medical devices. And the reason why they have been chosen and they allowed these to continue and thrive is that they preserve the molecular weight of the polymer and they allow to control the crystallinity. In other words, these are equipments that transform those tiny pellets, those grains of plastic, into a tube, like can be something like this or much smaller or significantly bigger, to be used, in our case, in medical devices and pharmaceutical equipment.
So, as someone coming from injection molding, like people usually have the notion, extrusion is a little more simpler than injection molding, since injection molding, you can make much more complex shapes. And, the connection with you has taught me is that is completely not the case. You can do a lot of very complex stuff with extrusion. And, it's not just a tube. It's not just, we have a cylinder and that is like pushed through a die, or a plastic that is pushed through a die, and then you have a tube, but you can do a lot more. You can have multilumen, you can have co-extrusion, you can have a lot more, let's say, much more complex things. So you might go into what, let's say, the complexity is of the devices and the shapes and forms and things you can do with your machines that like a simple extrusion cannot.
Let's say that you mentioned some macroscopic aspects, the shape, the appearance, eventually the surface. But there are several other factors that comes first, because when you put under control the microstructural properties, which mean the molecular weight, as I mentioned, which is the potential of the polymer, and the crystallinity, which is the actual configuration of the molecules in the polymer, then you can go on the shape and the continuous process. Imagine multilumens. If you don't have under control the parameters I just mentioned, they will shrink in an uncontrolled way. So they will be uneven along their length. If you think about balloon tubes, if you don't have under control those parameters, the tensile properties of the tube, artisan, before forming the balloon, and the mechanical performances of the balloon after having assembled it with the medical device will be out of control. And you don't want that. You cannot afford that, especially if you want to reduce the profile of the catheter of the device. Then you need to get the best out of the polymer because you want to use as least as possible. You want the thickness to be as thin as possible. If you want to do that and still have a safe device, you need to be very, very sure that the tube will not break outside of the normal operating condition, even if you go a little bit outside of the normal processing conditions. Of course, you don't want it to break or to perform in a wrong way within the normal processing condition.
So what you mentioned here is, like multi-lumen device. Like I have a very instructive tube in here. So this is a very, very thin tube, and it has 5 different. So it has 6 lumens actually. It's like it has a central one, and it has 5 one. So I probably, even if I hold it into the camera, like it's not even possible to get the resolution for this to be shown on camera. So it's extremely small what you can do. So it's very, very fine, let's say, geometric features that you can have here, and also with a very, very controlled geometry along the length. This is what the machine can do. But what fascinates me even more is, and this comes a little bit from the fascination of what I did in my master's thesis. So we initially wanted to do a 3D printer that can mix material properties along the extrusion length. And, like we figured it would be too difficult to figure out. So we went for something different, namely silicon 3D printing. What I've seen with the event that we recently did together, the medical tubing meeting on the Plast in Milan, is you showed me this. And this is a variable durometer extrusion. So this side of the tubing is more stiff than the other side of the tubing, and you can produce that continuously. And that is something that really fascinates me. So tell us how you do that, and why would you want such a tube that varies the stiffness along the length?
Pleasure. So again, thank you also for joining us at the medical tubing meeting. It was very important to have you there, and you've been very helpful. Thank you again. As I said, to put under control the extrusion means to be able to know how close what you are producing is to the drawing, to the specification that you were expecting. Dynamic extrusion to us came early as idea, so we started to play with this more than 30 years ago. The limitation that we found, and we still partially find, is in the materials available on the market that are not dedicated to this. You find a material dedicated to injection molding, you find materials dedicated to extrusion, to blow molding, but you don't find yet material dedicated to dynamic extrusion. We are working on that. And fortunately we have a very good set of relationship with the key raw material manufacturers, but this will be another topic if you like. Why people would like eventually to have this technology? This technology allows to alternate the material, as you mentioned, so hard and soft, and this means that you can have a soft tip which reduces the invasivity of the device, and the hard shaft right behind for having the pushability and that being able to introduce the device into the body. The advantage that we have compared to other processes are huge, because normally what you do would be to use a different section, different harnesses, but these expose the device to kink and oblige you to validate the welding or the gluing between the two sections. So why people would like to have this is for safety, first of all. I always like to think that everybody involved in the medical device industry does it for saving lives. At least this is what is at the center for us. So sustainable for us means that first of all, it's saving lives, and then it's done in a way that can grow over the time. Because if I don't do it in a sustainable way, I may do a life-saving device that nobody will buy, it will not go anywhere, it will eventually create frustration and loss of trust into the whole industry. But why to go in this direction? Well, first of all, in the medical device design, you can have differential hardnesses, conductivity, transparency, so differential function, and have what you need where you need it. Second, the reason why to use one technology rather than the other, well, I invite anybody that needs this technology to challenge the machine manufacturer in such a way that they will have the evidence that what is made is under control, that the process is not working for 10 minutes, 40 minutes, but is working for the full day. Because one of the issues with dynamic extrusion is that it's difficult to put under control one material. Is even more exponentially difficult to put under control when you alternate many different materials. I hope that I replied and I didn't went too much off track.
That is perfect. And I think, what you mentioned there, how currently minimally invasive devices, especially catheters, are designed and manufactured. I learned a lot from Damian Carr. Shout out to him at this point. He was also the one that brought us two in contact. So, thank you very much, Damian, if you hear this. And, I think it is always very striking to me as someone who comes from medical device that is injection molded, and not to insult anybody, but how archaic the current state of the art of manufacturing of these catheters is. It's like professional knot tying. You have a mandrel, then you pull out the liner over it, you make a knot in the perfect way, which takes you 3 months to learn how to properly tie that knot. Then you do your braiding, then you do your PBA outer layer, and then you put a heat shrink over it, and you shrink everything together so that you have your catheter. And if you want the softer tip, then you glue it on top of there, and you need to make the perfect cut with a razor blade so that it's perfectly perpendicular, else it doesn't work. So it's like a very, very manually driven manufacturing process, and it just strikes me as, there has to be a better way. And what I found is your machines provide a better way. So you might go into, how can we make this process continuous? How can we make this process, more effective? And what are the implications on, cost and validation if you apply something like a reel-to-reel production or a continuous production of catheters?
You took out twice the fact that people that has been interacting with you in the past about injection molding consider injection molding more complex. I don't debate about that. I mean, injection molding to me looks very complex. If I'm running the 300 meters or a marathon and I see somebody running for 100 meters very fast, I will always think, how can he do that? Because it's not my sport, it's not my area of expertise. So humbly, I think that is very complex. At the same time, especially in the world of today, what really matters is how you do things, because there is many ways to do something. So when you deal with injection molding or with extrusion, you can just copy paste something that somebody has done, or you can explore it and eventually go to the roots and reinvent it like my father did 40 years ago. So when my father made the first 10 millimeter extruders able to feed regular 3-4 millimeter pellets, he had to reinvent the extruder. It was not enough to scale down like many have tried the extruder. Our big extruders, 60-80 millimeter is the maximum that we do, which is a screw like that, are a scaling up of our microextruders that today goes down from 6 millimeter screw all the way to 80 millimeter screw. So what we do is to scale up the small one, because the small one has to deal with several complexities that the ordinary standard extruder doesn't keep into consideration. So the reason why I'm mentioning this now is what to focus on in order to improve any kind of process, including the dynamic extrusion. You need to understand the material. You need to feel like the polymer inside the flow channels. You need to understand that every time that the polymer slow down in a corner, it will burn. So if I have an edge and the polymer is flowing, trying to do this, what will happen is that by slowing down, it will take overexposure to heat, and it will eventually burn. Plus, I have the material slowing down here and the rest flowing. These will induce a friction on the below material, like the induced aerodynamic resistance on airplanes that reduce the efficiency of flying airplanes. So the key is to understand polymer. The key is to collaborate. The key is to find a way to openly innovate with other partners in the market and accelerate the innovation with the advantage of AI and all the new technologies. So it's very important to understand raw materials from the more intimate aspect of their identity. And so what we do is to, first of all, be curious. So to go deeper into the understanding the analytics over the polymer. So run any kind of weird test may give us some information about it. We exchange points of view with other people that may have the same problem we have, and we increase the amount of tests that we run on the polymer in order to correlate factors that we may not know that are dependent. So there are sometimes parameters that are measured and managed independently, even if they are connected and dependent. And there are other parameters that are not considered, even if they are independent and conditioning, maybe not on the short term, but on the long term. So what AI and machine learning potentially can help us into is to observe things that are too small or too big, too fast or too slow for us to observe and make experience on the base of the transducer, the sensor that we naturally have in our body.
I think what you just mentioned and what you just went into is, that you have to have the curiosity and baseline understanding of the physical principles that guide everything. And I think it's very, very important that, like, nowadays people think as convention as the limits of what can be done. And I see this very, very often in the discussion around sustainability. It's we have always done it this way is the biggest inhibitor of innovation overall. It's like a medical is very strong in this. It's like, because there's a good reason for it. Change is pain. Change is pain, and there's lots of work and lots of documentation and lots of processes associated with changing something that has worked before. So I think that is, the baseline of what a new technology or innovation has to be doing is having an understanding of the physical limits, because the laws of physics cannot be broken. Everything else, you might say laws can be changed, processes can be changed too, regulations can be changed, although pretty difficult to pull off. But this is where we should start, definitely the physics. But then the I say more business or pragmatically oriented people would say, I only care about knowledge as much as it helps me. Since, knowledge is a means to an end to do whatever I want to do, maybe save lives with catheters, and do that as efficiently and as safely and as sustainably as possible. So what I would like to go into is, what the outcomes of this understanding will be when we can do something like a variable durometer extrusion, inline braiding, and reel-to-reel production. What does that mean? Because, someone who's coming from a business perspective is like, okay, these are words that I don't understand. What can it do for me? And you might lay out how that would be looking and what the outcome of that would be.
So the integration of processes can allow the production of complex devices. Complexity is not necessarily a good thing, because the more complex is something, the higher is the number of things that can go wrong. The higher is the number of things that you must check in order for nothing to go wrong, and therefore higher is the cost. But in some cases, complexity is necessary. So the fear of the medical device in front of validation is understandable, but there are many tools for facing these. Process analytical technology, for example, is one of those. Instead of basing the quality on testing, base it on the design, base it on the inline inspection, the inline measurement. For example, who visited us at Plast show have seen that we are starting to integrate spectrometry inline with the help of a company called Colbistec. We have been scouting the market of inline spectrometry for a long time, waiting for something to be ready. And finally, we encountered this company that is populated by very nice people and is also very humbly facing the challenge of the inline spectrometry. Inline spectrometry allows you to look into the material. When you look into the material, you can say, okay, what is the key factor for this device to fail? So when I know what I want to achieve, I know what I don't want to go wrong. Then I have to, again, look into the laws of physics, of chemistry, into the model that allow me to understand that, because sometimes we call laws something that is very temporary, and in the civil world is okay, but when we connect this with nature and with the universe, then this may sound ridiculous to people in the future. Today we may laugh about when we think that somebody has thought that things were going in a certain way in the space, and today we know that it's not going like that, but they were doing their best. So today we should look with humbleness to any kind of understanding that we think we can have about nature, and keep studying with the curiosity and the devotion. So looking into the way that the chemistry is behaving or appears to be in our process, we can see, for example, that when the mechanical properties of a tube are damping, there is a spectrum that is changing. Nothing else seems to change, but this has changed. And we may easily neglect saying, okay, there was some noise, this has changed, but apparently everything is all right. But when I go to test the tube down the chain, maybe in days or weeks, I realize that something has gone wrong. And so if I recorded, which is what I invite everybody to do, if I record the whole process, I go back and I find a correlation between these two factors. And when I find a correlation, I know what to put under control. So if I have a chemometrical parameter under control, then what I can do is to say, okay, instead of just breaking one tube every 100 and have 1% of information, I can check the 100% of the production and make sure that this is not changing, because I know that when this is changing, the properties of the tube are going off spec. So putting this under control, I may not need to revalidate the process when I change something, because I know what matters. And this may conclude the nightmare of the medical device, one of the nightmares of the medical device industry, and facilitate innovation in there. This is what we are trying to pioneer, the increase of sensorization in the system, without expecting that the customer will buy the whole set of parameters. We do it first. We scout it. We invest on that. This is our duty. This is our job. So we find what matters to the process, and then the customer can buy a system that knows that is under control, independently from the extra test that they will run. This can be a redundancy at the end.
So what you laid out is, again, the importance of understanding your system and the importance of process validation and understanding with data-driven decisions on what matters in your process. So, and that means that, you need to do fewer revalidations, you have better quality control, and you have better safety of your devices. That is a very important point. I'm very happy that you went into that. The question was also more aimed towards, what can you do in terms of scale and commercial, let's say, cost or sustainability improvements when you do continuous production of a catheter. Because as I laid out, these catheters are usually done manually. And that also means that you will shift production to low wages countries, it usually to get it somewhat cost effective. If you can automate such a process, you can run it near shore and run these processes very close to where the R&D is, which in turn I think will, number one, improve not only the economics of the thing, but also the sustainability and the innovation. Can you go into like how can we produce a catheter on a continuous basis? How would that process work?
Okay, so Hormuz's crisis has shown us that to produce in a different place is not necessarily a way to make more sustainable anything. So the point is that in a world that is changing, equilibrium and key factors of the determining the cost of something may change. So when we integrate a process, we reduce the domain of the post process. Why post process is not process? Because there is some logistics involved. Every time that you have logistics, anything can pretty much happen because the level of accuracy in logistics is much lower than the level of accuracy in the process itself. So when parts are moved, when they are in a cardboard box, they are expected to be safe. But if this cardboard is subject to temperature changes or mechanical stress, I may not know what happened on the inside. So if the process happened in chain, is under control. I reduce the out of control steps. Imagine frozen food. If the truck goes off power and the food get unfrozen and refrozen, I may or may not realize that this has happened, but the food may become unsafe. Same thing for the device when it's produced. So if I connect one ring to the other, the process can potentially be implicitly much safer. Plus, every time that I open a cardboard box, there is somebody that has to check that things are in the same place where they stopped in the previous process. So somebody has to put them in a box, somebody has to open the box, somebody has to validate the outgoing quality, somebody has to validate the incoming quality. These are parasitary costs. And when people are afraid that there is a loss of job because of automation, they should consider that there is nothing worse than living a life doing a boring work. So automation allow potentially people to grow. Of course, people has to will to study, need to have the will to understand, and this is the difference between just relying on weaknesses or relying on strength. So our approach is in the medical device where the life of somebody is on the other side waiting for a life-saving device to always do better. So to always study a better way, to always commit more to a better result and so on. So putting under control the process, putting in chain, our final target is the dark factory. Dark factory because if you put people in the same environment where machines are, you end up having an environment that if it's good for people, it's somehow toxic for machines. If it's good for machines, it's somehow toxic for people. Think about temperature. Think about moisture level, light, presence of microwaves, of micropowders. So things that for a machine can be vital or non-dangerous, for people can be toxic and extremely dangerous. So people and machines should not coexist in the same environment, especially when this can be avoided. And robotization and data-driven processes allow this to happen. So costs and efficiency are strictly related to the coexistence of processes and functions, machines, resources that should not be in the same place.
Are you a medtech company and you want to make your device more sustainable, but you're not really sure how? With the link in the description, you can now book your free consultation. Click the link, find a time that suits you, and show up with your questions. We're here to help. Very interesting points. And I think also as someone who is like more practically oriented, and this is what Damian told me, and you can like validate this or not. Like his estimation was that if you switch from a like completely manual process of assembling a catheter to real production, which is basically continuous production of a catheter. So you would co-extrude, then you would braid in line, then you would extrude another layer on top of it, and then you would have the reel of a continuous catheter with the exact right properties. He was estimating that that can like cut the cost by like a factor of 4. It's like you have 25% of the cost that you had before. Of course, you need a bunch of equipment. Of course, you need to validate a lot of processes, and it is extremely complex to get the machine right and to get the process right. This is why people are usually refrain from it, because we've always done it this way. We've always done it this manual way. But I think what we need to put in front of people also is not the pursuit of knowledge and wisdom, but also the carrot that you can achieve with it. And I think if you tell a business you can cut the cost of your device by a factor of 4, that is something that people are very, very interested in doing. You will also reduce a lot of scrap. You will reduce a lot of sometimes fluoropolymer use. It's a very big discussion in medical tubing right now. What do we do with the PTFE liners and all of that stuff? So I think you might comment on that one, and maybe also a little bit on the PTFE side, if you have any insight on that. And then we will talk a little bit about other topics.
Sure. So definitely, this statement of factor of 4 on cost coming from Damian is for sure a well thought point of view. If I would say it, it may sound like I'm trying to sell a technology, So I refrain from giving expectations on that. Also because I know how dependent this is on several factors that are out of control. So we have been speaking in the last minutes about the advantages of the more extremes of the industrialization, robotization, data-driven process. I still think that the full manual process has huge advantages. The artisan approach put a person at the center. So when this person is responsible about what he's doing, can be much more accurate than any machine so far, because can still decide to say, okay, I don't like this, I toss it away. The machine is not really free to do this autonomously. Okay, the machine is a gear of a process that humans invent. There are advantages and disadvantages. Cost. The cost of an industrial process that is going out of control, that is not properly managed, at the end can be much bigger than the cost of an artisan making them slowly, one by one, but perfect. There is a lot of waste, unfortunately, in the industry in general, not just the medical, into every industry. Typically, the big waste is connected with the automation and out of control. So when something is partially done by human and partially done by machines, you are walking on a land that is not in control of anybody. Like I said before, to have the coexistence of machines and people in the same space can take very fast the worst out of both sides. If this is done for cost reasons or for greediness, if you have people and machine working together for improvement, then you can take the best out of both. I have a friend in New Zealand, is the director of a big company doing, let's say, food containers. And there is the first time I've seen people working with machines taking the best out of both. And the reason is that people were not afraid to lose the job, because the governance of that company is not just promising to people that they will be not laid off when robots will do their job, but is explaining them why they will not lose the job. So humans can speak to each other and understand and decide to trust each other. Machines cannot really trust each other. The trust of machines is a default. When a machine is giving an information, the other machine is taking it as granted. People has the ability to discriminate in a good sense. Discriminate means, to me, to recognize the difference between things. And when this is done properly, this is the most powerful thing that people can do. And this is what we should never forget. So to be able to recognize the level of trust we can give to an information we are getting and work for improving the prospective level of trust of the inbound and outbound information is a key factor. So going on cost, what can really be appealing for the market is to know that when a process is under control, so is well sensorized, is robust, it doesn't spoil the molecular weight of the polymer, it allows to control the crystallinity, and is also allowing the dynamic extrusion, and is doing all of that with an interconnection going from raw material manufacturer all the way to post-processing like tip forming, RF welding, braiding, whatever comes later, allows potentially for a huge cost saving connected to the reduction of hand-to-hand verification, so logistics in between, and outgoing quality check, incoming quality check. These are costs that you cut immediately. Plus, when the process is going slower, there are more analytics that I can put in line in order to assess the quality of my product. So the quality assessment, frequently done by 4-5 people doing the same job, checking the same thing, can be fostered to a machine doing the boring part of the job and the people checking if there is something else wrong. This will give a total quality control on the part. So more safety, better use of people. Machines cost once when you buy and you install them. Then we could talk about programmed obsolescence. That's another topic. But when a machine is a good quality and you can assume that its lifespan will be covering the whole range of payback time that I programmed and maybe further, then I know that the investment will be paid because the promise will be kept. So if I have one machine working with another machine, working with another machine, there are all a series of costs that may be even higher than 4, but it has to be calculated from case to case. What we can for sure promise is that our machine is so sensorized, so robust, so well thought that it can connect with another pair, so another well-designed machine, and they can cooperate and work together in order to save all the cost deriving from waste, scrap, inefficiency in between the two processes.
Just a small comment on the second question on the topic of fluoropolymers and how you see that as fluoropolymer replacements. Have you seen the possibility to get rid of fluoropolymers? And maybe another question is, what is very much suspected and not very much known in the industry? There are certain parent polyfluorated alkyl substances, PFAS, that are also used in, machines. Especially, I know that in injection molding, like high temperature lubrication, is usually done by PFAS substances. Number one is, do you have any dependencies in your machines on, PFAS substances, and how do you see, the replacement of fluoropolymers?
Now, people were not in need of medical devices and, of course, of fluoropolymers 300 years ago. And in the 14th century, 15th century, we had the Renaissance. So people can make beautiful things without fluoropolymers. That's a short reply to your question. In medical device industry, it's always possible to find another way to do it. Before using PTFE, something else was used. So we can step back. Politicians and people, bureaucrats, had to find a way to cope with the contingency. So the problem with fluoropolymer is coming from several reasons. Greediness. Do things for making money even if it's not under control. We see this a lot in the run to space. People want to go in the space today because of greediness and ego, and they don't care about the pollution that is generated just because we are not yet able to do things just right. Okay, so with a little bit of patience, sometime you avoid to make stupid things today that could be better tomorrow in a more sustainable way. The problem with the fluoropolymers is that they've been used for spraying on cardboard of pizza boxes. And when you spray something, you make microparticles. Those goes in the water, and if it's PTFE, it stays for millions of years stable. Okay. What's the problem of stability? We don't know yet. What is the problem of microplastics in our body? We don't know yet. That's the problem. That since we don't know it, and somebody found them, and there is a lot of hysteria around plastic, somebody have to find a solution for keeping people calm and for avoiding that people feeling are represented does things that are making even worse the situation, like strikes or sabotage to facilities that are not doing anything bad, but if there is a sabotage, they can emit pollution into the environment. This kind of things has happened and keep happening. Every war is a natural disaster. Okay, so with this said, PTFE used in a solid form doesn't cause any harm to the environment as far as I know. But again, it's about what do we know. During the synthesis of the fluoropolymer, if the process is not under control, things may go wrong. So under control, process under control. Try to take unexpected factors out of the equation. People are introducing wonderful unexpected factors into the equation. But when they are into the equation, you cannot separate the unexpected factors for a process that needs to be based on well-paced phases. Okay, so I think that in the next decades, the production of fluoropolymers will be more and more under control and will not stop, because by the time that somebody will try to fade it out, there will be new uses of fluoropolymer that will justify their presence into maybe processes that today we don't know yet. And there will be an increase, an improvement on the stability. Today we have people advocating for nuclear. A few years after we had Fukushima, a few years after we had Chernobyl, you cannot compare the damages of fluoropolymers with the damages of nuclear. So the damage of nuclear are much worse than fluoropolymers, but nuclear is still a topic. So fluoropolymers will be still a topic. I don't see why fluoropolymers should be given up.
I think it's about doing it responsibly. And I think I really like that your take that process needs to be under control. It's like what do you really have to give, the PFAS ban activists, if you want to call them that, is that the production of fluoropolymer has polluted a bunch of landscapes very badly. And it's not that the fluoropolymer per se is unsafe, as they are, because there's also an FDA letter on this. And it's like we think fluoropolymers are safe and they're going to be around for some time. However, it's like the production of the fluoropolymers has caused a lot of environmental harm. And then on the other hand, what also is the case is we have been using fluoropolymers for some applications where they're just, an overkill and not necessary. And I've found a bunch of applications where it's actually just used because we've always done it this way. And this is also a theme that comes up a lot. There are certainly applications where you need all the good properties of fluoropolymer, but there's definitely also applications where you don't need them, and therefore like a justified and well thought through material selection needs to be done. So going a little bit into another topic that you're very passionate about is, something that you would call augmented intelligence, not artificial intelligence, but, augmented intelligence. Explain why you think that term is better and what you mean by it.
Sometimes I like to provoke, I don't like to take as granted definitions. I think that when you create some confusion around definitions, you reestablish the freedom of people to call things in the way that they feel. I mentioned before another word, discrimination. Discrimination today is one of those words that people doesn't like to use, and it's a pity because all of our evolution has been based on discrimination. It's the use of discrimination that can be wrong. So if I use discrimination, which is my ability to recognize the differences, for excluding somebody, I do something wrong. But if I use discrimination for improving the quality of the life of everybody without excluding, but rather including what I'm missing, then I'm doing a good use of discrimination. So why I don't like the definition of artificial intelligence? Because people are scared. And I don't think that they should be scared about the name or about the appearance it has. There has been many things in the history where somebody gave a scary name to something, people started to fight against this, and they got distracted from what was really the problem. So if I give a scary name or an appealing name to something and I make it scary, people will focus on that. And a person with bad intention can go behind them and do whatever he wants. So let's continue to think about computer, about digitalization, if you like, about innovation. Let's leave aside the word artificial intelligence for a moment. What has the computer been used for the last decades? They have been used for helping us in doing boring things, repetitive things, things that we were not good at. So we have been using artificial whatever for helping us in innovating, in living a little bit better. Like you said before about fluoropolymers, sometimes they are used in places where they are not needed. So to spray PTFE on the cardboard of pizza was done because somebody had this spray in his hands and then said to his friends, hey, this doesn't allow cheese to stick on the cardboard. And everybody started to do it. And this was a poorly thought thing. This has happened many times. Think that the dishes in the Roman era were covered with lead paint, and when they were putting vinegar, they were producing lead acetate that was tasting good, and so this spread. Everybody started to use lead paint for food container because when you would put vinegar, they would taste good, but it was toxic. Okay, same thing about the spray with the PTFE today on the cardboard. Just stop doing it. Okay. And this was the root cause of the problem. But sometimes this is also what is allowing us to make a mistake. Why do we know about this problem? Because this has happened in US, because this could have happened in Europe. And people measure the toxicity, people measure the contamination today. We measure the pollution. So thanks God we are in Europe, thanks God we are in US, thanks God we are in places where somebody is taking care about us. And we should feel happy and satisfied about this. And instead of going in a public place with a cardboard thing on myself, not doing anything else than just spreading the word of somebody else that is just maybe trying to distract me, let's study where the problem is and let's look for solution. Frequently, people going with a cardboard thing in a public place are students, so study, find a solution to the problem. This is not a solution to the problem. Maybe I would put this plate on me. This is not a solution to any problem. So when I was a teenager, I was passionate and I did this as well. At that time, it was important to try to do it. Today, to the young people, I say what old people were saying to me. Maybe many young people will not listen to me, but some young people will listen to the fact that this is not solving the problem, but studying and not be afraid to communicate, to share, to take your position, not be afraid to lose your job, not be afraid to look like ridiculous. These are things that changes really the world if you study, if you practice, if you burn your finger, if you cut your finger trying to do things. So now let's go back on AI. Why AI should not be scary, either you call it artificial intelligence or augmented intelligence. Because we can still and we will always be free to work without technology. 1,000 years ago, people created the base of what we can do today without the technology that we have today. So in 1,000 of years, somebody will benefit out of what we did with the technology we have today. Let's use it. Let's use it at its best. But let's try to find a way that is not comfortable. It always has to be a pain. You spoke about the pain of the medical device industry when they have to revalidate, okay? Part of this pain is due to the fact that they delegated too much. So I see sometimes under weak control on certain dangers in processes, and I see an overexcitement about other things. For example, there is an overexcitement about burning finger. So hot surfaces look like a radioactive problem. And this is a problem itself, because people have to be more and more far away from the machine in a period in which we still expect people on machines. So the reason why we are looking into the dark factory is because I always tendentially look at the phenomenon and say, okay, how can I do my best in order to harmonize this trend into the real world? So if people taking care about health and safety assessment doesn't want for other people to burn their fingers, given that I think that is a very healthy thing to burn your fingers because you learn to do better, while if you don't burn your finger, you don't learn, and you may continue to do the same mistakes over and over, but that's another story. People are free to make mistakes. People are free to burn their fingers. People are free to study a better way to do things. And if they use AI to simulate scenarios, they can do this even faster, and they can experiment on new mistakes, new errors that they never did before. So augmented intelligence, I like to call it in these ways, because it's an artificial intelligence that is borrowed to me in order to augment my ability to foresee and to test and to design things that I don't have the time to. Imagine a humanoid that cut the grass into your garden instead of you. Is a duty. Somebody find it relaxing, somebody like to do it, but not everybody. I personally consider this annoying because I don't like to cut grass. I like it to grow in the way it's naturally growing, but that's my point of view. So if I really have to mow my garden for making my wife happy, I would rather give it to a humanoid to do rather than doing it myself. So augmented presence on the earth. This is another way you can call it.
That's a very, very good example. It's for the tasks that you were anyways not good at, did not enjoy, and it helps you take over these tasks while you can focus on, other more value creating tasks. I think that is a very good way of putting it. Very good. So, Simone, what advice would you like to give to our listeners in terms of microextrusion, dynamic extrusion, and what you can do with the modern technology of today?
Be curious. Don't be afraid to lose your job in an industry that keeps innovating. Help it to innovate. Don't be afraid to lose your job because you want to experiment something that is not dangerous for the patient. Of course, I'm talking about R&D, and everything has to be traced, declared. So people should communicate more, exchange more, participate more. I frequently hear, oh, I cannot participate to this conference, to this event, to this show, because the company is cutting on traveling. Okay, do it with your own money, because you are a person that wants to enjoy your day, wants to enjoy your work. So if we participate to bad habitudes, then we cannot complain about the results. Today, revalidation of a process is a nightmare because too much has been delegated. And so people taking care about health and safety has taken too much control sometime over processes that still need to be improved. But if you tie your ankles, you cannot walk anymore. And if when you cannot walk, you cannot generate value anymore, then the whole company is endangered. So of course, people, safety first. So people doesn't have to hurt themselves. This is of course at the base. But I also have to think that people are not stupid, and normally they are not masochists either. So people doesn't want to hurt themselves. Of course, I'm talking on people on this side of the process, not the patient that is maybe lying in a bed waiting for a therapy, but I'm talking about people on a process. People can hurt themselves. Pinch your finger is not killing you. To burn your finger is not killing you. So health and safety people should maybe touch the processes a little bit more, should be more curious and less arrogant sometimes. And people on the process should be less scared about challenging procedures in a constructive way, not in a rebel way, but in a constructive way, and use more the what if and can I? And the reply, no, you can't. has to be painful for the one saying, no, you cannot. So you have to challenge. The world needs the market needs that. We all need that, because today we are frequently trapped in situations in which I have solutions for, which is the dark factory. The dark factory may cut jobs in the short term, but in the medium term will, of course, improve the quality of the process and the industry. If somebody is concerned about losing his job because of automation, because of technology, well, this person should study, should challenge the process itself, should find a way to make it safer, better, and more pleasant at the same time. What we should never do is to sit down, sit back, and relax, thinking that things will go well anyway without our help. Everybody that is doing something, everybody that has a job can improve the industry in which he's operating, no matter what is his job. Is either it's directing and managing something, either it's controlling a process more or less valuable. Everybody can change the world.
I think that's a very, very motivating last few words. Do you have any other last words?
I think I spoke already too much.
Very good. So thank you very much for coming on the podcast, Simone. This was Simone Maccagnan from Gimac International. Until the next time.
Grazie. Ciao, Lucas.
I hope you enjoyed this episode, and if you did, share it with someone who can derive value from it. And let us know in the comments if you enjoyed it. If you still have questions, use the link in the description to book your free consultation. Click the link, find the time that suits you, and show up with your questions. We're here to help. Thank you very much for watching, and until the next time.